So in this talk, I basically want to cover two things. The first will be what my definition of machine learning is and what some of the basic paradigms are. There will be about this much math in the whole talk, and that will be towards the beginning. And so that's kind of the general framework for how people usually approach and set up these kinds of models. And the second part of the talk will be kind of about current issues in machine learning. So these are some of the things which the research community has been very focused on recently. You may also have noticed in the past few years the news media is increasingly paying attention to AI, machine learning, these kinds of buzzwords because of things that have happened in society in terms of unfairness, in terms of data breaches, in terms of privacy and security concerns. So we'll speak about some of those things. And at any point, if someone is confused, you can raise your hand and I'll follow you. So please be interactive. So to start, as we were discussing just at the beginning, machine learning is sort of defined differently by different people, and actually it's really, really empirical in practice. We have some idea of what our approach is and what our framework is and how to set things up, but once we actually want to get a model working and have it tell us useful things, we end up having to try several parameter values and pick the one that works well, and we may not know why it works well. So the joke in the community is it's something like this. Yeah, so you just stir the pile until it starts looking good. So anytime you hear someone talk about how machine learning is so magical, think this. And then the broad applicability of machine learning is also important. If you have a lot of data, then maybe there's something in machine learning for you. This is also why I think everyone should have some basic literacy in this subject. So you've probably all heard of artificial intelligence. That's really broad field. I actually have no idea what AI means at this point. People use it to describe so many different things. Machine learning is a subfield of artificial intelligence. Machine learning is essentially about learning from data. You have a data set and you want to extract a pattern, usually in the form of a model with certain parameter values. Deep learning is also getting a lot of hype right now. Deep learning is part of machine learning. I'll go over what the differences are. Things like regression and classification, which you've seen in statistics, they're kind of both in deep learning and machine learning. You can use deep networks to do these things. There are also other methods, support vector machines, recommenders, decision trees, which are very intuitive. There are Bayesian methods. So I'm not going to talk about much probability today, but Bayesian methods are an example of where you need a whole lot of other math to have kind of the same setup to solve different kinds of problems. And other stuff. So the point of this slide is really that this field is very big and some people use deep learning when they mean machine learning, some people say artificial intelligence when they mean deep learning, so just become comfortable with the idea that people will use these things in different ways. Just try to understand the main points. Yeah, so these are all kind of blurrier than I'm actually proclaiming them to be. So within machine learning, there are two basic types. There's supervised and unsupervised learning. We'll talk about supervised learning today because when we're looking for a pattern in the data, supervised learning is concerned with correlating inputs and outputs. We want to learn a model that learns how to correlate inputs we give it to outputs that we think are right. Unsupervised learning would be just the inputs, but today, inputs and outputs. So like I said, ML is all about learning from data. So we begin with a data set, always data. That's the first requirement. And some kind of question, some kind of pattern we want to look for. And we train a model to correlate the outputs with their corresponding inputs. And this model is usually, we say what the model is, and what we actually end up training are the parameter values. So we actually have to guess and say, oh, I think a regression model works here, now let me tweak these values. Or I think this kind of neural network architecture is good for this problem. We'll try to train it and learn all the weights and biases. So you do actually have to start with some kind of model that you think is applicable. And then after training it and adjusting all its parameters, you test and evaluate it, and then maybe you go and apply it in the real world. So this is kind of the machine learning workflow, the most basic workflow that anyone would need to set up a problem. Can you still hear me, Clay? These are all examples of pictures you might see as being associated with machine learning. So probably you've seen some kind of neural network stuff with all the circles. That's just a pictorial representation of a lot of functions being composed together. Something like linear regression technically could be machine learning as well. Support vector machines based on linear separators. That's a Gaussian mixture model. That's sort of from the more probabilistic side of machine learning. And then finally on the bottom right is clustering. So clustering is actually unsupervised. Clustering is just based on inputs. But again, all of these things part of the field. It's a very broad field. So let's think about this workflow a little more. So as an example, I want to go through a really simple model and show you each of the components of this workflow with respect to this model. So let's have a really, really simple regression model. X is our input, Y is our predicted output, W and W naught are our parameters, say weights and a bias. So, and the data is in the form of these pairs. So this is supervised learning. We have to know in our data set what the pairings are. We have to know this input goes with this output. So the form of the data set is X, Y pairs. Any questions so far? So we want to be able to evaluate this somehow, so we need some kind of loss or error function. In this case, for regression, let's do something very simple, just square error. So we have the y hat, which is our prediction based on the model, so based on the green parameters, which represent the model. And we have the actual known y from our data set. And the difference between those tells us how good our prediction is, right? How close is our predicted output to what we know to be true. So we can evaluate this. We have the model. And then we can see what the error is. Any questions about this? So now the question.
The error log is always observed.
The error is always observed. The error. So we have to choose some kind of error function. It may not be square error. We have to choose that just as we choose the model. Observed as in we always. When we consider the error, we have to consider the predicted output and the actual output in the case of supervised. So in that sense, observe from the predicted. So now the question is, we have these W and W naught parameters. We have those as soon as we decide what the model is, right? As soon as we say, okay, let's use regression, we have some weights and we have some bias. Now, how do we make those good such that we get good predictions? This is the question of optimization. So machine learning, most machine learning uses gradient methods. You may have heard of gradient descent. So the basic idea of gradient descent is that we know we want to improve the parameters of the model, W and W naught. We also know that when our predictions are good, the loss will be minimal, right? If our prediction is very close to the actual, then actual or predicted minus actual or actual minus predicted, it's close to zero, right? So that's good for us. We want low loss. So now the idea is we start with some parameters and we make small changes to them in a clever way such that we get minimal error in the end in our final training. Does that concept make sense? Small changes is the part. So the idea of a gradient descent update is we have a notion of gradient from the error function. So the error function has the parameters of the model in it, it has the predicted output in it, and it has the input in it, and as well as the actual output. And so the gradient is just the multidimensional slope of this with respect to the parameters which we care about. So we can give at each time step a different point from our data set to this, and to the model, and then look at the gradient of the error function with respect to the parameters which we care about. The idea of gradient descent is that you have some kind of error landscape, some function which describes your error. And you want to move around in that landscape such that you find a low point where the error is low. So the idea of gradient descent is that we want to go downhill in every dimension. Each parameter is a different dimension. And so each dimension will have some slope, the error slope with respect to that dimension, and we want to move downhill in all of those dimensions. That's the sort of concept. And so to do this, we take very small steps of size gamma, which is quite small. We have our gradient, and the update for any given parameter is is simply that parameter at the previous time step minus the gradient with respect to that parameter times the small step size. So this is the notion of taking small steps in a good direction to make the error lower than it previously was. Any questions on that?
So are you saying that at every timestamp you take the previous gradient and apply it to the next?
Yeah, so at every time step we fix a point that we're considering. We do this stochastically. We say pick this point randomly from our data set. We feed that point into the model, evaluate the gradient, that value, the gradient with respect to the parameters we care about. So yes, so this gradient is, actually this should be t minus 1.
Yeah, T minus, that's why.
Good catch. Yes, this is t minus 1.
So the previous sample, right?
Yeah.
How do you avoid open minimum?
Great question. Empirically. So in this kind of scenario that we've described for a regression model with square error, it's very, very easy because it doesn't actually matter where I am. My parameters, I can start with anything for my parameters. And as long as I take steps in the downhill direction with a small enough step size, I will eventually find the global minimum. There aren't any local minima in this case, so convex error functions make it very easy. So this example is straightforward. You can have the same thing in 2 dimensions, but it's still convex, so you can still start anywhere and you will go down using this method. There's also this notion of splitting our data set. So we're given some data set up front, but we're not allowed to just use all of it to teach the model something. We can only use some of it. The other part of it has to be kept for evaluation purposes. So we train on maybe 80% of what we have and test on the remaining 20%. And the reason for doing this is these models are often very complex, and so we don't want to have the scenario in which it's simply memorized every possible example that's seen in the training set. We have to make sure there's some unseen data on which we can evaluate the model's performance. Otherwise, we don't know how it's actually working. And then to your point, there is a reason more complex models are difficult to train. It's because there are local minima. So if we compare something like this easy parabola to something with global and local minima, then it's very possible that we could easily get stuck somewhere. And now the place in which we start, the initial parameter values are very important. You know, if I start in this valley and go down, I'll end up here. But if I start in this valley and go down, I'll end up here. Maybe one is significantly better. In that case, people play around with step size, they play around with how long they train for. With a larger step size, I might have the possibility of jumping out of a hole given a certain data point input, which is why we choose data points stochastically as well for each time step. So this is where it starts to get really empirical. Like the whole reason that all of this theory falls apart very fast is because for the kinds of models that people are considering today, which are very complicated functions, the error functions are also very complicated. Those landscapes have a lot of places in which you'll get stuck and it won't be workable. So a lot of the challenge of training is simply about not getting stuck. That's most of the challenge of training, especially for people.
So what does getting stuck mean? How do you define it?
Getting stuck means my step size is such that I converge to some local minimum, which is actually not good compared to the global minimum, which exists. And in practice, I mean, you might never find the global. You have to sort of decide what is good enough for you in terms of accuracy.
But that tolerances set can change.
What can change?
The tolerances set. If you set some like
For given your error function, you have some error that you're willing to tolerate. Sure. All of that is up to you. Most of this is up to you. It's just the approach that's
that is not really fixed in time.
no, it doesn't. Your step size also can change with time. That's not.
So
don't know the global minimum, how do you know that you're stuck in this?
You're getting something bad.
Compared to what you think we are.
What you think is good. I mean, it's very hard to have absolutes for this. The other thing about the complicated models is that you might have hundreds of parameters, but most of them are zero. So you can actually have a lot of models that look very, they might have looked very different in the beginning, but once you train them, they're actually all they learn the same thing. Their error landscapes might be similar. But the thing is, you never have an absolute. You have no indication. Even if you do hit the global minimum, you don't know that. So when I say these complex models, I'm talking a lot about deep learning. So this kind of diagram, it's just a function composition. So this part here, this is just a linear combination of input variables and weights. In this case, it's a fully connected feed-forward only network. At the blue nodes, we usually apply some kind of nonlinear function. This is a somewhat recent innovation, this idea of applying a nonlinearity, because it lets you have much more expressive power in your final function. So if we were to write out the equation for this, it would basically be a linear combination with nonlinearity applied to it, plus a linear combination with a nonlinearity applied to it, plus a linear combination with a nonlinearity applied to it. All of that has some linear combination with other things and other nonlinearities. And there's a lot of stochasticity here given our initial parameter settings, right? We have to start with something. If we started with 0, the gradients would never move. So we have to start with something that actually randomly is often used. There's a lot of work on what good initializations are for these models, because actually no one understands why it's good. This is, again, a very experimental part of the field. But the main idea that I wanted to convey here is that these complex models are just complicated functions, which are made of simpler functions all composed together with some nonlinearities. And of course, these complicated functions, since the predicted output is considered the error function, all of these would have very complicated error functions as well. And that makes training. So here's a fully connected feed-forward network. This is kind of the earliest one, the first thing that you learn if you take a class in it. People used to use these without the nonlinearities, so they were just complicated linear combinations a long time ago. This one is a convolutional network, so this is what you typically use with images. The advantage being that you consider small sections of the image at a time and move across the image. And as you do this, you have the advantage of preserving any kind of 2D structure which is present in the image. So if we do something like this on an image, we actually have to flatten it and consider every pixel separately and log them here. In this case, with the convolution, we can actually have a window that considers 2D structure. So that is why it's thought to be really good for images. This is a recurrent network, so this is storing some idea of state. So you can implement like a state machine using a recurrent network and take the previous output as one of the inputs to consider. This is useful when you're modeling sequences. This is, you heard of DeepMind? They built an agent to play the game of Go a couple years back. This is what their networks looked like. And their model was a lot more complicated because it used the idea of rewards to train on what good moves and good trajectories were. And so that made these models, again, they were using convolution, they were using state, they were using recurrence, as well as this kind of simple function composition. So all of this is deep learning, and deep learning itself has a lot of other fields. And usually there are certain models that are more applicable to certain kinds of data, such as images or audio or just numbers. So we went over this.
I'm gonna have some coffee.
You guys don't talk. Okay. Any questions so far?
What?
You sure? One thing I just wanted to mention is that we talked about square error in the case of regression. That's sort of very easy. You might wonder that, you know, when I have these more complicated functions, how do I figure out the gradients? Right? This is sort of doesn't that suddenly become much harder? So yes, you're right. It is harder, but it's still possible. We have this non-linearity. Usually, people use value. It's like for linear rectifier, basically. So anything that's negative goes to zero. Otherwise, it retains its value. This is typically the non-linearity that's used in neural networks, and this is kind of innovation in deep learning. People tried it, and it actually worked really well. So this is the non-linearity which we're applying at each of these, well not here, but each of these nodes in the group here. So remember I was saying we have a linear combination with a non-linearity applied to it. This is the non-linearity which is typically applied. And you know, this could suddenly make taking the gradients a lot more difficult. Right? Taking the gradient of a linear combination is easy, but taking the gradient of the linear combination with some non-linearities and then composed with other things, you might have the intuition that this is harder. It is harder. How do we do it? So let's say we wanted to optimize for this parameter. So this is a weight early on in the network. We want to optimize its given the error gradient with respect to it, right? That's what we want. How do we calculate that, right? Our error, this is our, our output y. So we're going to calculate our error using this, and we somehow want to take the derivative of that with respect to this thing way over here. We want that. We have to use chain rule. So again, straight from calculus. Based on your network structure, you have to set up the chain rule such that you can get your parameter gradient from the error. So I just wanted to say, this is all still possible. The framework which I described is still possible and done even when the functions become very complicated. Because in principle, it's the same thing. Questions about that?
Yeah, assuming reversibility here.
Reversibility. I'm assuming that I can take the derivatives. So I'm assuming it's differentiable. Yeah.
But sometimes it's not really. You got mixing, let's say what a bit mixing.
Okay.
So for process, you cannot
Um.
here we go. The chain rule here is not assuming.
Well, I'm not actually. When I'm doing the chain rule here, I'm not reversing anything, right? If I can take, like, say this gradient I can take easily, right? I'm just looking at the derivative of this parameter with respect to this one, and I know the function which relates to it. So I can do that. Same thing here. I know the function which relates the output y to this parameter. So I'm actually not assuming reversibility. I'm just assuming knowledge of the function. But you do need to be able to calculate the derivative. That is that much. These are just some examples. I'm not really going to go into detail on these just because there are so many. So like I said, these convolutional networks are typically used for images, such as, is this a cat, yes, no, or what kind of animal is this, cat, dog, horse, whatever. MIT recently had some success with a breast cancer prediction model, which again was image-based and used convolutional neural networks. So medical data in the form of images is another place where convolution is being applied a lot. And then recurrent neural networks are used for audio, typically. That's what you need. In audio, sequence and state is very important, right? A sound followed by the preceding sound makes a lot of difference to a current sound. That's the important.
What are those used to? voice signatures?
Yeah, I mean, you can talk to your phone now, right? And it knows what you're saying. This sort of thing. Game agents. So in the research community itself, companies like DeepMind, one big thing that they love to do is train agents to play games and beat humans at them and achieve this kind of superhuman sportsmanship of that game. And they often do that using reinforcement learning. So reinforcement learning is based on these same ideas, but also incorporates kind of a world state with all the possible states you can be in, all the transitions you can have, and all of the costs or rewards associated with particular actions or trajectories. So there's a lot more that goes into that model, but it allows you to learn very specific good things to do. And the reason it works so well for the games is that if you're playing against the human has some limitation in how many possible combinations they can make. They may not have a good intuition about, how many steps ahead they have to plan for. Now, given computational power and the ability to know what a good trajectory is, it becomes very easy to be a human. And I should also point out that this is very, very different from Deep Blue, which was the robot which I think IBM built, that beat a human chess player, Gary Kasparov. So in that case, that was a brute force algorithm. The complex, the chess, and it's sort of computationally infeasible to compute very far ahead. So it was a good challenge for the people interested in game agents to take up, because any solution, and specifically the solution that they had, was not a brute force approach. They were not considering every possible combination. They were saying, they used probabilistic approaches as well, because all of the transitions in the world are probabilistic. But they basically figured out which parts of the game space are the most interesting to explore. And those are the sequences of moves that should be considered. And learning which parts are interesting all comes from the notion of having costs and rewards. So this is the wide area of reinforcement learning, having these additional costs and rewards and some world which are modeling. It's also, it comes from robotics actually. That's where the whole world modeling comes from.
But if there's a small probability, if there's one path among a million paths that gets you to the right answer, that has high cost, will it ever be chosen? You don't know that initially.
But is it a good idea to take that?
We don't know.
Initially, no. So initially you're exploring, right? Initially in any kind of world model, you have to explore to get any kind of information about what costs are out there. It also depends on how many steps you have. If you limit it and say, you have to get me something in 10 steps, then maybe it'll never find this really special one point that you were talking about. So there's other considerations. You're saying, how does it learn this is bad?
Okay, let's say I would go from point A to point B. And there's a huge mountain in between.
Okay.
Right? All other parts, and this is actually the shortest distance.
Okay.
All other parts have planes,
Okay.
but the paths to go there are really long.
Okay, so you're saying the only option that you have that will work looks really bad. So you have to do enough exploration such that you learn it's better than the other things. This is also where the idea of having a horizon comes in. If I have to get something after a certain number of steps, then I just have to make sure I have enough steps for it to learn that I can actually get something positive in the end. In this sort of a situation though, you would have to do a lot of exploration just to learn that this is the only way. One thing which you could change in this model is that, say you have rewards, it's a reward model, use both positive and negative rewards. So instead of having it be neutral, have these other spaces be negative. And that way, as you explore them, they become more and more negative, so you stop exploring them. And eventually, you find only the good one, and that's the best one. So using both positive and negative rewards in your model is a way of speeding that up. But either way, you have to do a lot of exploration in your scenario.
But then, if you only follow the path where the probability of winning is the best, doesn't it become predictable for the person, like which way the like can you like create like a very predictable path, like a very good one, so you know that the machine will go into that path.
So you're not necessarily choosing that I'm going to follow this whole trajectory regardless of what the human player does, right? You're evaluating every time it's your turn, what is the best move for me right now. We call this a policy. So the policy is what is learned by the game agent, and the policy says, given this state, this world state, which includes the other player's position, my position, maybe some history, what's already happened, given that current state, this is the optimal action. So it's always considered on the basis of it being your turn and what your policy is. And as you continue playing, your policy may be updated.
But like it feels like a human player could artificially create like a right nice path for the machine to follow, and just at the end change something and like win.
That probably depends entirely on the game, right?
Yeah.
So it becomes very specific very quickly. I think the idea is that you explore enough of the world that you sort of understand everything which can happen. Oh, there's an interesting anecdote actually so when AlphaGo, which is DeepMind's agent, was playing Lisa Mural, who's the Go champion. AlphaGo won most of the games. I think Lisa won one game. And in the one game which he won, it was after a game that he had lost. And in the game he had lost, the computer had done something that looked absolutely crazy to him as a human. So if we are training our agents to beat humans, when humans do things that seem crazy to humans, the agents get confused too. So the subsequent game that he won had him doing things that he also sort of wouldn't have done before. But after seeing what the agent did, he thought, wow, that's crazy, maybe I can try that. And the agent hadn't caught up. It caught up in the game after.
Yeah, because it didn't have this type of data.
Yeah, exactly. So there's this kind of back and forth also between game agents and humans. Like, we think we can make them superhuman smart, but all the data we're giving them comes from human. There's a little bit of a back and forth. Oh yeah, I just wanted to show something fun which I made. But my excuse for showing it is that I want to show the level of detail you can achieve with some of these very complicated models. So this is a photograph that I took, but I did something to it. I applied the style of a famous painting to this photograph. Does anyone want to guess the painting? Yeah, sorry, it's anyway. So this is my original image, and of course that's the painting. And what I did here, it's called a Mural style transfer. We are able to train a neural network to preserve the content of the original image while adjusting it to give the style of the style image. So this is sort of how fine-grained you can get with something like images. And the other sort of very good thing about deep learning for images is that before, when people in computer vision tried to make sense of images analytically, they would look at things like edges, they would look at things like shape and lighting, which are all very meaningful and specific features or aspects of the images. Here we're just looking at pixels. Our model is complicated enough to just slide a window across pixel values and make something of it. And the fact that we don't have to make explicit features is, it saves a lot of time and effort and money and lets you kind of throw your data blindly into a model, which in some ways is good and in some ways can be dangerous. But this is sort of an example of the level of detail and fine-grainedness you can get.
The style here is defined by you as.
Yeah, so you set up your objective and loss functions to maintain this content, but give this.
Can you give a couple of parameters in the gradients of colors?
Yeah, it would be based on gradients of colors, and it looks like position because you see like this part of the image looks like it's also kind of here, so position is also here. In this case, you're tweaking pixel values. This one maybe doesn't follow the pipeline I described earlier, but it should give you a sense of what can be changed. I wanted to just briefly talk about like who gets to use machine learning in the first place. Does anyone have any ideas about this? Who's using it in the world?
everyone.
Okay, fair. People with large labeled data sets, in the case of supervised learning. Well, so labels just mean corresponding outputs. So in supervised learning, you must have labels. Those with high computational power. So when my dad talked here about data centers, this is what he was talking about. You need a lot of compute in order to perform all of those matrix operations, all of that optimization. You're running this for a long time. If I try to do this stuff on my laptop, it gets very hot. So maybe I use a GPU or I use an external server somewhere. And of course, those who understand the concepts and tools, those who are comfortable with programming frameworks, those who use math, that one is a given. So I think we're doing really well on this one. I mean, there's a lot online. You can go and look. You can learn so much just from Googling things. These two, I'm a little more worried about. So, large labeled data sets. How many of you have Instagram? How many of you have ever hashtagged something on Instagram? Instagram thanks you for giving them lots of nice labeled data. Right? When we think about how we use social media these days, we're actually creating a lot of labeled data. And of course, that one company has all of them. So if I wanted to do something studying how certain images are on the platform, then I mean, if I have access to the data, if I can somehow collect it all, then I can answer that question. But otherwise, I don't have that. What about like the Aadhaar card? Right? Who has all of that data?
UIDA.
Yeah, only them. Right? So we can't do everything they can do because we don't have all of the same data. High computational power and capacity. Amazon, Google. Pretty much it. It's getting to the point now where a lot of machine learning research can no longer be done in academia. It has to be done at a company because they're the ones with the data sets and the computational power. And if you want to be a PhD student and do it, you better go intern at Facebook. Otherwise, they'll beat you to your result because they have more computational power. They can do maybe the same thing as you but faster. So this is kind of the state of the research space right now. People in research maybe understand this stuff really well, but without these essential resources, you cannot solve problems involving huge amounts of complicated data. So of course there's this whole question here about the democratization of technology, and who has access to these things and how power maybe is distributed or not. So this is important to mention, I think, in any kind of discussion.
Methods being developed to do research environment, new methods.
They are, but if they're methods that rely on a lot of computational power or being able to experiment a lot. Remember I said it's very experimental. I might try 30 different approaches and have one of them work well. Now, in order for me to be able to try 30 different approaches in a reasonable time span, I need a lot of compute. So I'm better off doing that at Mural or Facebook. So it does, in some ways, it is all about resources. The deep learning community is also, it can be very secret because you might be trying something and if word gets out that you're trying it, someone with more resources might do it faster and be used to paper. This is actually how people think.
Google and Microsoft are also providing clouds.
Yeah, so some companies are paying a bit of lip service to the idea of democracy. They are making certain computation resources available. So Google's actually, they have something called Colab, which is what I use to do the neural style transfer. If I had done it on my laptop, it would have gotten very warm and I wouldn't have been able to do anything else on it for 2 hours while it was running. So I was able to do it on a Google server for free. So there are sort of some resources that are available for free, but they're all available by the benevolence of these companies. So whether that's sustainable is also an important question. Okay, so this is kind of the second part of the talk. The technical details and intuition and issues were what we covered. We can talk more later if you want to know anything else. But the research community recently has had a big pivot towards social and ethical considerations. Maybe, do any of you maybe know like examples which have come up recently that you remember? Cambridge Analytica. Okay, so this is data privacy.
Google having that talk with the booking a saloon thing.
Google Assistant sort of emulating a human
human.
and speaking to humans who are potentially deceased. Yeah, so should we do that just because we can? So there's always this kind of a question with technology. We very much have this question with machine learning as well as lots of other considerations. So the kinds of questions we have to ask are what kind of domain-specific knowledge must we consider? So for example, when I'm trying to work on climate modeling, I have to stop every 10 minutes because I don't know something basic about climate science. It's definitely not the case that computer scientists can just go into the world and fix everything for everyone, right? We have to immensely respect the domains that we're trying to go into. And historically, computer scientists haven't always been great at respecting other disciplines. We have to ask ourselves whether the output of this model is directly affecting humans and how it's doing so. Is it in conflict with existing legal or social structures? And are we concerned about bias? Like bias in the data, right? If we're training an agent on human behavior, it's going to learn only from human behavior. And like say an alien shows up and plays Go in a different way, maybe the alien will win. So yeah, this is something that you should basically always be thinking about when working with really any kind of data, but especially in the context of machine learning where you have the potential to amplify things that are bad. And this has really exploded in the research community recently. So this is like the number of papers on fairness and bias in machine learning. And you can see that in the past several years it's really gone. This is a good thing. Here's a nice example. This one comes from Moritz Hart, who's a professor at UC Berkeley, and he has a fairness in machine learning course that he runs there. This is from one of his blog posts. So it's a Gaussian mixture model. It comes from a probabilistic model. We don't really have to care about how it's trained using expectation maximization. But say we have this data set, and we can see that in these two dimensions there's some kind of separation. There's a majority of points over here, and just a few points over here. Does anyone have any observations about the model fit around the points? So I'd say maybe like the green is the actual and the red is the model fit. Or maybe any observations?
The data points are too less.
Okay.
Data points for the one that's below.
Yeah, so there are far fewer data points.
Far fewer.
What about the model?
When you have lots of points, the model and reality fit well, and when you have just few points, it doesn't work.
Yeah.
Even if it's the same model.
Yeah. Okay. Now, what if I told you that all of these points represented a human somehow? Would you be concerned? No one's concerned.
What's the context?
That matters, but even just given the information that each model represents a human, and humans in whatever minority this happens to be, don't get as good of a result from this model. I mean, is this discrimination? Is this illegal? Maybe that depends on the context, but there's certainly bias that's already evident, right? If you're modeling based on your aggregate data set, the minority will always have over time.
This data was also in the other data?
This is one data set.
So they separated.
Yeah, it's a Gaussian mixture model, so they can have things, but it comes from the same data set, the same training process. Another issue, so the US has a lot of racial disparities. There was a ProPublica expose a couple of years back that found that a predictive software tool that was used to assign recidivism risk, the risk that someone will go and commit another crime after being in jail, after being arrested. It was found that the false positive and false negative rates were unfairly distributed across race, black and white in this case. So this is an example of a model working not as well for a certain group. Now, whether it's because it was a minority or because the data itself is biased, if people who are, racially biased are creating the data set, are doing the arrests, giving the sentences, creating all of that labeled data, if that has the bias, well then the model's doing the right thing, it's just learning the bias which is there in the data. So this is a huge, huge issue. I mean, we get really excited these days about having cheap sensors, having online platforms, having all these sources of data. We're so excited now that we have all this data. And sometimes we're too accepting of it, right? We have to question the data itself. Is it the right thing? Are we going to learn the right things from it? So this is really important. I won't even go into the sort of legal aspects of that, but you can imagine there are many. Another issue that we have right now is interpretability. So when we talk about these deep models, we think, oh, they're really great. They work on images that we don't really know anything about other than their pixel values. That's great for us. But when we want to understand why a model made a decision that it did, it becomes a little bit harder. Even if we have transparency in the sense that we can see what all of the parameters were in the trained model, we don't know what that means necessarily. Right? It's just pixels and weight. I don't know intuitively what to make of that. So this is a lot of something that's being worked on a lot in computer vision. This is Richie's model. This is a decision tree. So this comes from the climate science project I talked about on predicting regional rainfall patterns in the Indian monsoon based on sea surface temperature. So here, the inputs were sea surface temperatures from different regions of the oceans. And the tree actually tells us, oh, this one at the top is important. And it means that if it was warm over here or cool over here, then we would be closer to having this kind of a pattern. And then based on that and something else, we would take this branch. Another example of this would be in medicine, in clinical medicine and diagnostics. You first consider some set of symptoms, then based on that you might consider some other symptoms, and then based on that you might make a diagnosis. So these are the kinds of models that we are maybe used to seeing as humans. They fit with our natural pattern. There's both interpretability and explainability. I think the main difference is just that with interpretability, we're looking at whether the model itself gives us some intuition. With explainability, it's a little bit more about, is there some way we can ask or probe the model after it makes a decision to get it to tell us why it made that decision? But people use them together. There's kind of some in-between work. So this is an image that we're looking at midway through the training process on this image. And if we look at sort of where the signal is the highest, where we're getting these larger parameters, we see that it looks like it's got heavy signal on the edges in the picture. So that much makes sense. So there's research being done in computer vision that looks at these kinds of mechanisms and sort of ways we can visualize and interpret these models. Oh, this is a fun one. How many of you have heard of the trolley problem from philosophy? Okay. So now with autonomous vehicles, we no longer have a human driver. We may, in some situation, have to pick between two unappealing decisions. How do we code them? I know it's been suggested, just the people who are in the car, you put them in danger, everyone else makes sure they're safe. Then would we want to go in such a car? So this, maybe even if the trolley problem itself doesn't come up specifically, the trolley problem is basically, there's a runaway trolley on a track, and the way it's currently going is going to hit and kill 5 people. I am there as an observer. I have the option of diverting it to a different track. On that track, it will kill just 1 person. Should I intervene and save lives, or let it be and let more lives be lost? This won't come up exactly with autonomous vehicles, but the situation of 2 unappealing outcomes certainly comes up. I don't know if there's really a good resolution for it. The one that I've heard when I've asked people who work at these companies, they usually say, do the thing you're when you have two possible outcomes, they're both being predicted. Like in our models, we're predicting, oh, we're going to hit this thing or we're going to hit that thing. Go for the one with sort of less certainty to happen, because it might not happen. That's the result.
And also there's issues like when there is a human driver, when you have the choice between two independent solutions, the driver doesn't have time to analyze the situation and choose. So even if there is no perfect solution with autonomous vehicles, maybe it would be less bad when the human driver, because sometimes we may be able to choose like less independent solution.
I mean, if we were only holding autonomous vehicles to the same standard as humans, we should be replacing humans now. They're already better in good conditions. The issue is that we are holding autonomous vehicles to a much higher standard than we hold humans to, at least in terms of accidents per kilometer or per mile. Also, the fact that AVs and human drivers are mixing is hard, and then of course road conditions, weather conditions, other kinds of traffic that are there. Like, it's going to be different in Mumbai than it is in Mountain View. So all of those things are important too. So yeah, there's this sort of regulatory and legal question of how do we code these things? What should the right answers be? It's really not obvious. Oh, this one is fun. This is another example of how data that exists in the wild or in the real world comes out and shows bias. So, study, researchers trained a word embedding model. So, word embeddings are a way of representing vocabulary in high-dimensional space. So, as letters. And this study found that extreme she occupations included homemaker, librarian, nanny, nurse, housekeeper, socialite, etc., etc. And extreme he occupations included maestro, philosopher, financier, magician, fighter pilot. So clearly there's some gender bias here. And this gender bias was not injected by researchers at any point. It wasn't, these people being sexist. It was actually there in Google News and the kinds of examples that we see in the world. So they came up with a way to de-bias it, basically by introducing more constraints into the model. So we know it is sort of technically possible to at least start addressing this kind of data bias once we know that it's there. But if you think about kind of how the world is biased, that is reflected in the data sets that are there. Healthcare disparities. So I talked about racial disparities in policing and criminal justice. Similar racial disparities exist in healthcare. For example, in this breast cancer study that was done at MIT, one of the major successes of it was that it works equally well across different races. But it's only black and white. Like, I don't know how it would do on South Asians, for example. In this case, I think they simply made sure they had a diverse enough data set that it was fine. But if you look at, for example, some of the sequencing companies that are out there now, you can send some saliva, get your genome done, and they tell you stuff about you. So those don't always work as well for people of certain racial and ethnic groups because the data set to which they're comparing everything is mostly some other ethnicity. So this has medical implications as well, because some populations are more predisposed to certain kinds of diseases, like heart disease, or conditions making you more likely to get oral cancer. So if these considerations are not represented in the data set, maybe you have to incorporate them somehow separately. But these are the things you really have to consider if you're trying to help. Like if you're trying to do something actually impactful in society, then you have to consider all of these things too. And then of course privacy and security. So we talked about Cambridge Analytica. There's a lot of talk now about facial recognition. I mean, countries are using it, police departments are using it. Regulators are kind of catching up. Like one of the cities, not Cambridge, but a city near MIT, just completely banned it recently because it was being used. There's also this, there was a health controversy with DeepMind. They were trying to help out in the UK and they were building an app that the National Health Services was going to be using. But then it sort of came came out that they had gotten a bunch of data that maybe they shouldn't have had access to. And so someone is on leave over that right now. Genomic data is also becoming really popular. The company that I'll go and work for after this is relying heavily on this. But there's of course a huge privacy and security concern. If someone has your genome, there's a lot that they can do with that. And it's not just about identity theft. It's not a lot of information that they can continue to mine once it's out there.
Talk a little bit about Grail.
I haven't started working yet, but sure, yeah. So Grail is a startup in the Bay Area. They spun out of a genomic sequencing company called Illumina, and their goal now is to develop a blood test that will be a routine and relatively inexpensive blood test that will screen for early signs of cancer. And the underlying science is that usually cancer is bad because by the time we've detected it with any kind of symptoms, it's already progressed so far that all of the existing treatment methods are either not really going to work anymore, or they're just so expensive that only rich people can afford treatment anyway. So the whole idea of the material of the tumor will spread to the bloodstream before the cells of the tumor actually spread to the bloodstream. So if we can detect this very tiny signal of genetic material in the bloodstream at an earlier time, then we can detect cancer early. Of course, we have to figure out all kinds of things like what is the mutation, is it in an important place along the genome, what is the tissue of origin, what follow-up tests are necessary, what is the patient's profile health-wise, what's their genome, how do we sort of compare the reference with other genetic material that we found. So it's a complicated human biology problem. It's also a complicated computational problem because genomes are very large. And then it's also a complicated ethical problem, how to appropriately handle this kind of data, how to have security around it, how long do you keep people's genomes stored for this kind of thing. So there's a lot of dimensions to these approaches when you actually want to use them to do something helpful.
The type 1, type 2 errors in this kind of decision will be very different than
Sorry. Type 1, type 2 errors.
False positive, false negative kind of errors.
Yeah. Yeah.
What you do with the diagnosis.
Yeah, I mean, I think in this case, it's maybe not good to scare people and tell them they might have cancer, but it's probably better to ask more people to do follow-up testing than to say, oh, it's probably fine. But yeah, humans are still the ones making these decisions in the end. I don't know how they're currently doing it. Like I said, I haven't actually started working there yet. It's kind of funny thing right now in the industry about ethics boards. So companies are trying really hard. Maybe they are actually trying really hard, but they're also trying really hard to give the impression that they care a lot about ethics and society and these things. So a lot of them have joined, consortiums saying they care about society, or they've endorsed some general AI principles that sound very idealistic. And some of them have ethics boards. The thing is, we almost never know who is on these ethics boards, what they actually do, what kind of oversight they have, and how it impacts products. So it's good that we've started talking about it, but I think until we have laws and regulations around it, it's not necessarily meaningful. So I would be a little bit skeptical of these kinds of things in the same way that I would be skeptical of, having computational resources by the benevolence of companies. So I guess the main point that I wanted to make with the second part is that, machine learning is a super interesting and wide technical subject, but if you want to do anything interesting with it, you really need to know more than just the technical aspects. You need to be able to work with people from other domains, you need to be able to think about societal and historical contexts, and you need to sort of retain humility. You're not going to solve everything just because you know some math. And so I think the popularity of machine learning is going to keep going up because we just get more and more data and we want to make more and more sense of it. So the natural thing to do is to throw our models at it. But we'll have to become more and more critical of how we're doing this. Otherwise, as we've seen, it has the potential to be bad. So, but it also has the potential to be good. So, it's technology. It can be either. We have to be careful about how we're using it. And then I just wanted to include some more resources online that I think might be interesting to people. Here, I'll just put everything up in case you want to take a look at it. So, Andrew has a machine Coursera. I think it's free. Universities also may have like some machine learning lectures and problem sets and other things that are out there. So it's definitely, like, if you want to go and learn all the math and the models, you can do that online for free. There's a fair ML course at Berkeley. So that one I think also has all the materials online that'll give you some idea of how people are approaching it. There's also research literature on this stuff. Frameworks, I mean, everyone knows like TensorFlow, Keras, PyTorch, these are all in Python. We use for deep learning. So Python's becoming really popular. Machine learning is one of the things it's very popular for. So those are deep learning frameworks. There's also all kinds of other mathematical and statistical frameworks that people use. Even like MATLAB has some deep learning packages now. Google Colab, so this is it's an online in-browser notebook environment in which you can code and execute scripts. So you can make images and save them. You can run sort of maybe like power-intensive scripts that if you ran them on your own computer, it would take a long time, but when you run them in browser, it actually runs on their servers. And so it finishes much more quickly and your computer stays the same production. So Google Colab is really, really nice. And it's good for like quick prototyping and experimentation as well. The AI Now Institute in New York, so this was started by Kate Crawford, who's a sociologist actually. She comes from a social sciences background, not from math, not from machine learning. And she was actually the keynote speaker at one of the biggest machine learning conferences just a few years back. So this tells you that like the research community is attempting to take these issues more seriously. So they put out a lot of interesting kind of social science research on AI. They do a lot of these, we think this might be an issue, so let's do an expose on it, or let's try and explain how we split the issue. So these kinds of things are, good to have on